All right. Good morning, good afternoon, good evening, everyone, wherever you are. My name is Stan Chung, and today I'll be presenting our work on heterogeneous III-V silicon non-volatile photonics, the Mach-Zehnder memristor. So I'd like to thank all my colleagues listed here for their contributions and also RPE for funding our work. So I'd like to first start off with the base technology platform we've developed at HPE for optical interconnects. As we all know, silicon itself is a poor material for realizing stimulated photon emission due to the indirect bandgap nature of the material. Therefore, we wafer bond III-V materials such as gallium arsenide or indium phosphide to produce lasers and SOAs onto a silicon platform. So we also utilize the same platform to create ultra power efficient metal oxide semiconductor capacitors. So here's a diagram of our process. We first start off with two wafers or two samples, III-V, and also the soy. We either do a O2 plasma treatment, or you can do a CVD SiO2 deposition, do a CMP, but we typically do the O2 treatment, and then that creates a highly reactive OH bonds, and then you place the two wafers together. You do thermal compression bonding from anywhere from 250 to 300 degrees C. And if the bonding is free of any bubbles or defects, you can remove the substrate. And what you're left with is a thin film of active layer or indium phosphide. So we've developed a comprehensive portfolio of heterogeneously integrated devices on a common silicon platform. And that includes lasers, high-speed modulators, and MOSFET phase tuners for filters. So for the microring laser shown here, we've shown tunable lasing wavelengths with ultra-efficient phase tuning. The MOS capacitor is shown where this yellow box is. We've shown leakage current anywhere from 20 to 50 femtoamps for a plus minus 4 volt bias. And that leads to 5.3 nanometers per picowatt. And that versus thermal or carrier injection tuning is more than 1 billion times improvement in energy efficiency. So likewise, for the micro ring modulator here, we've demonstrated static BPIO numbers of 0.12 volt centimeter with 1 nanometer of tuning for a 4 volt bias. And these eyes here show 25 gigabit per second modulation, both at 20 degrees C and 80 degrees C. We've also used these MOSFET phase tuners to correct for phase errors in our deinterleavers and filters. And the left graph here shows that without phase tuning, the extinction ratio for these cross and bar ports are about minus 7.3 to minus 10.7 dB. Now, with a minus 2 volt bias, we can dramatically decrease crosstalk down to minus 16.4 and 27 dB, respectively, while consuming only 10 nanowatts of power. So as you saw in the previous slide, at the heart of wavelength tuning in our devices is this intermediate oxide layer between the III-V and silicon, shown here in this TEM image. And the oxide we typically use is aluminum oxide or hafnium dioxide, or a combination of both. Now, what if we can actually somehow incorporate memory into our photonic devices? And so as it turns out, through an electroforming process, a high electric field across the oxide can cause non-volatile switching. So it turns out the oxide-based non-volatile switching is something described as a memristor. It was theorized by Leon Chua in 1971 to be the fourth passive circuit element, and combines the word memory and resistor. Now, in collaboration with Leon Chua, Stan Williams at HP Labs, he experimentally demonstrated the memristor in 2008 using titanium dioxide. So the memristor is actually nothing new to HP, but as photonics guys, we were unaware that this device was already a byproduct of our process, which is convenient. In this particular device here, you see there's a 40 nanometer cube of titanium dioxide consisting of 2 layers. The lower layer has a perfect 2-to-1 oxygen to titanium ratio, making it an insulator. The upper layer is missing 0.5% of oxygen, which makes it more conductive. Now, if we apply positive voltage on this blue electrode here, the positive oxygen vacancies are repelled down into the insulating titanium dioxide layer below, and that increases the conductivity of the entire switch. So negatively, or a negative voltage pulls back the positively charged oxygen vacancies, and that makes the switch more resistive. Now, what makes the switch non-volatile is that when the voltage is removed, the oxygen vacancies don't migrate. So as a result, the IV curve will show some sort of hysteresis as shown here. Okay, here I'll talk about what goes into our low power MOSFET phase shifters. So our single mode structure is shown here. The wafer bonded 3-5 silicon region is a moderately doped 150 nanometer thick gallium arsenide layer. Here we have a cross-sectional SEM image of the device, and over here is the TEM image of the bonding interface. And for this particular image, a combination of hafnium dioxide and aluminum oxide was used. So this figure here on the left shows a simulated effective index change, which corresponds to the left axis, and associated free carrier absorption losses on the right axis for a range of bias voltages. So this is done for several dielectric thicknesses of aluminum oxide. The same is done for hafnium dioxide over here in this graph. So to put these values into a V pi L figure of merit, if we assume a length of 500 microns, an aluminum oxide thickness of 5 nanometers will have a static V pi L of 0.13 volt centimeter. Now for a higher K dielectric such as hafnium dioxide, a thickness of 5 nanometers will have a static V pi L of 0.09 volt centimeter. Okay, so here we compare experimental and simulated refractive index changes of our MOSFET structure. So we've actually fabricated our devices on a platform with 3 different variations shown in this graph here. But this plot down here shows calculated index changes of various aluminum oxide thickness versus bias. And we compare that to measured results indicated by the purple squares. So it's quite close, but the measurements point to either an effective index thickness of 15 nanometers or a different refractive index value. Likewise, for hafnium dioxide over on the right, measurements indicate either a larger effective thickness of the hafnium dioxide aluminum oxide stack or a change in the refractive indices. So we're currently investigating these with TEM imaging and CV measurements. So in this slide, we'll show the optical response of the 3-5 silicon MZI under non-volatile operation. So we first bias the device from 0 to minus 20 volts, and we keep track of the IV and the optical spectrum. So I've color-coded the spectrum to the IV operation to make these things easier to see. So when we set the device right on this IV curve, there's more than a pi phase shift. In fact, we see a redshift of approximately 14 nanometers. Now, if we turn off the device indicated by this orange line here, the spectrum, doesn't really change at all. In this case, it changes about maybe plus minus 0.2 nanometers, and this indicates an electrical optical non-volatile correspondence. So in this slide, we make an attempt to try to reset the device with a positive voltage, going along the IV curve indicated by this green arrow over here. We see that we can electrically reset the device. Now in this reset state, the spectrum continues to redshift, and then it finally blue shifts by 4 nanometers. So nowhere near the original spectrum. Right now, we don't know why we can't optically reset the device. So we're in the process of investigating interfacial chemistries with TEM and EELs or electron energy loss spectroscopy experiments. So here we take a look at some time duration tests. The red curve over here is the initial state with no bias. And the gray curve here shows the case where we bias up to minus 10 volts and then turn the device off. We then take data every 5 minutes for 24 hours on optical spectrum analyzer. As you can see, it remains quite stable. Next, we bias up to minus 13 volts, indicated by the blue curve, and do the same thing, and it's stable as well. So we can track a particular resonance dip and plot out its variation over time, and that's what we do here. X being in minutes, and then the Y being in wavelength. The set state is stable by plus minus 0.05 nanometers for 24 hours and probably even longer. And it seems like we can tune for a desired wavelength, and really we have phase tuning with near zero static power consumption. So next we wanted to see how much these phase shifts correspond with the change in group index. So we can do this by tracking the free spectral range for each bias point. And the graph on the right here shows that we see about a 0.01 change in group index, which is quite significant. So again, we're currently in the process of evaluating our TEM and Niels experiments to determine what can give rise to such a large index change, as well as the non-volatility behavior. So here in this slide, I just wanted to add something about new avenues for neuromorphic photonics. There's been a lot of work out there on this subject. Shen et al. Showed that a network mesh of MZIs can be used to create an optical neural network, and they demonstrated vowel recognition. Perez et al. Showed that a hexagonal mesh of MZIs can be constructed such that programmable photonics can be used for optical routing or optical filter synthesis. So here we list some of the features of current neuromorphic silicon photonic prototypes. Waveguide losses are about 0.1 to 1 dB per centimeter. The 2x2 gates are typically MZIs. They also have some loss. These are also based on thermal tuners, and they consume milliwatts of power each, and are quite slow. Most of this is based on linear processing. And let's see, there's no high speed or low energy non-volatile memory. But using our hybrid 3-5 silicon on the same silicon platform, we can enable higher speed modulation, on-chip gain, and light sources. Also, with the gain, we can enable 3-5 nonlinear processing, and also fast and low power non-volatile tuning elements. In summary, we've demonstrated a non-volatile 3-5 silicon MZI with a direct electro-optical correspondence. We saw a greater than pi phase tuning for near zero power consumption. The physical mechanism for set reset states is not fully understood, and we're currently investigating that. And we're solving, and also by solving the reset issue, I think that can lead to new avenues and architectures for neuro-inspired photonics. And we also have additional classes of non-volatile lasers and ring resonator weight banks. And those are currently in progress by my colleague, Bassem Toussaint. So here are all my coworkers and collaborators. So I'd like to thank them. So that concludes my talk. And I'm open to questions and comments now. Thank you.